Hello and welcome to this presentation on Newton's method in Python. So let's get started. What is Newton's method? Newton's method is an iterative algorithm used to find the roots of a differentiable function. It was first described by Isaac Newton in the 17th century. The method is based on the idea of using a tangent line to approximate the function near a starting point and then finding the x-intercept of that tangent line. Newton's method can converge very quickly to the root if the starting point is chosen carefully and the function satisfies certain conditions. However, it can also fail to converge or converge to a different root if these conditions are not met. Therefore, it is important to use caution and understand the limitations of the method when applying it to a particular problem. Coming on to the next slide, this shows how the convergence of Newton's method is possible. First, we find the step size which is equals to f dash x upon f double dash x for a univariate function, and then according to the step size we get nearer to the minimum or the maximum point. This is what is displayed by this picture. Coming on to the next slide, the convergence rate of Newton's method is generally considered to be quadratic. As you can see from the given formula, the step size is nothing but minus of f dash of xn divided by f double dash of xn, where when we have to minimize the function then f double dash should be greater than 0, and when we have to maximize the function then f double dash of x should be less than 0. The formula given in the slide comes from the Taylor series derivation. Coming on to the next slide, let's talk about the convergence rate. The convergence rate, as I already discussed, it should be quadratic, and specifically if the method converges to a root of a function f with a non-zero derivative at that root, then the error in the approximation after n iterations is typically proportional to the square of the error after n minus 1 iterations. That's why the convergence rate is considered to be quadratic. um, Talking more about it, this means that if the initial guess is reasonably close to the root, Newton's method can converge very rapidly with a high degree of accuracy. So this is how efficient Newton's method is. Coming on to the next slide, what can we do for multivariate problems? I have already submitted the source code where I have tried on multivariate problems like Rosenbrock's function. So this was discussed there. And whenever we set Newton's method or we create a function for a multivariate problem, we have to find the gradient as well as the Hessian matrix, and then we can find the convergence point, and the gradient and Hessian matrix can be found using certain Python libraries that we already discussed in the source code. Coming on to the next slide, this is the multi-dimensional example, multivariate problem, Rosenbrock's function. And as you can see, this is how the function looks like in 3D. And this is the black dot is the convergence point for this Rosenbrock's function. And this is considered a valley because there is depth in between two heights. So this is kind of a parabolic valley because it has a shape of a parabola. Coming on to the next slide, the advantages of Newton's method can be many, such as rapid convergence rate, efficiency, since Newton's method requires the evaluation of the function, its first derivative, its second derivative at each iteration, so it is very efficient. and versatility, because it can be able to find the roots, it can be able to find the minimum or the maximum point. Also, it is able to find these for the univariate or multivariate functions. It has a high accuracy, since if the initial guess is chosen carefully, this method can achieve high accuracy with small number of iterations. So also this can be particularly useful in applications where high precision is required or high accuracy is required, such as in numerical simulations or scientific calculations, or where certain data is required more accurately, like nuclear reactors or some chemical labs. Overall, Newton's method is a powerful and versatile tool for finding roots and maximum and minimum points of any function due to its rapid convergence and high accuracy. Coming on to the next slide, what are its applications? So, Newton's method has its applications in machine learning. Particularly, I have explained here logistic regression, where we find the maximum likelihood. So, what is maximum likelihood estimation? The parameters of the logistic regression model can be estimated using maximum likelihood estimation, which involves finding the values of the parameters that maximize the likelihood of observing the observed data. Newton's method can be used to solve the optimization problem involved in MLE, which is maximum likelihood estimation. Specifically, Newton's method can be used to iteratively update the parameter estimates based on the gradient and the Hessian matrix. And as I said before, that the gradient and Hessian matrix can be found using certain Python libraries. Also, the application of Newton's method in logistic regression has many benefits, like faster convergence, robustness, because Newton's method is less sensitive to the choice of learning rate than other methods such as gradient descent. Because in gradient descent, we choose our own learning rate, whereas logistic, no, in Newton's method, it has an adaptive learning rate which changes every time. So there is no need to keep a learning rate of your own. It can detect its own learning rate with each iteration, and hence can prove to be more efficient since it would reach the convergence point quickly. It has high accuracy again. So overall, Newton's method is a very powerful tool which can be used for many machine learning applications. Here I have used the example of logistic regression, but it can be used for many other machine learning algorithms like binary classification, multi-label classification. Also, it can be used in k nearest neighbors to find the value of k, which gives us the minimum error value. So this is how important is Newton's method. Thank you.